Hello. In the previous lecture, we proved Galois' solvability theorem, at least one direction. What is the statement? It says that if f is a field of characteristic 0 and small f is a polynomial with coefficients inside the field capital F, suppose K is a splitting field of this polynomial over the base field capital F, then if the polynomial small f is solvable by radicals over the base field capital F, and this should be emphasized. So if it is solvable by radicals over the base field capital F, then the group of F automorphisms of the splitting field K is a solvable group. And let's recall that a group is called solvable if it has a chain of subgroups such that the factors of each one by the next one is an abelian group. Now, today we are going to use this theorem and show that there are some polynomials there are some polynomials with coefficients inside Q that are not solvable by radicals. There are some polynomials of degree 5 that are not solvable by radicals. To do so, we need to have a better understanding of solvable groups. So we start with basic properties of solvable groups. Suppose I give you a group G and I tell you that it is solvable. Then every quotient of G is going to be solvable. So if N is an arbitrary normal subgroup of G, then G over N is also solvable. And every subgroup of a solvable group is also solvable. So if H is a subgroup of G, then H is also solvable. Moreover, if I tell you both N and G over N are solvable groups, then G is also solvable. So here in the last part, I'm not assuming that G is solvable. So for the part 3, let's change this maybe to instead of G, I'm going to use another letter, let's say M. So M is a group, and I'm telling you that N and M over N, both of them are solvable groups. In that case, we can deduce that M is also a solvable group. Okay, so these are the statements that we want to show about solvable groups for now. And okay, so let's start with first part. Knowing that G is a solvable group means I have a chain of subgroups starting from the group G, going decreasing chain of subgroups. So G1 is a normal subgroup of G0, G2 is a normal subgroup of G1, and so on till I get to the trivial subgroup. So I have a chain of subgroups, each one normal in the previous one, and the factor of G sub I by G sub I plus 1 is an abelian group. That's the definition of being a solvable group. Now, knowing this, I want to get a similar chain for the quotient of G by N. So the natural thing to do is to start with the natural quotient map. Let's denote it by P sub N, that goes from G to G over N. So this is the natural quotient map that sends every element G to the coset that's represented by G. So I start with this natural quotient map and I apply this group homomorphism to all the elements in all these subgroups in the chain G sub I. So we get the chain of subgroups starting from P sub N of G. So let's denote it, let's write it down. So I get P sub N of G naught. And because G1 is a normal subgroup of G naught, P sub N of G1 would be a normal subgroup of P sub N of G naught. And I continue like this. So we get this chain of normal subgroups. So as soon as we show that a quotient of two consecutive subgroups is an abelian group, we are done. So that would imply that G over N is a solvable group. Okay, so we get the result as soon as we show that P sub N of Gi over P sub N of Gi plus 1 is an abelian group. But what does that mean? This means that when I pick two different cosets of P sub N Gi plus 1, then I need to show that they commute in this quotient. Okay, so let's see what it means. Let me see. So this we have actually argued earlier, that whenever I tell you that a group quotient out by another one is abelian, then when I apply a group homomorphism to the quotients, I will get again an abelian group. This we actually argued in the previous lecture. Let me show you the relevant lecture note. Okay, so it is over here. Yes, it's over here. So this is exactly the statement that we proved in the previous lecture, that P sub N G sub I over P sub N G sub I plus 1 is an abelian group. And essentially, we say that if I give you two cosets, I'm allowed to flip the order. And in order to detect this, we flip the order, and then we look at the inverse of the flipped order multiplied by the usual order, and we have to say that it is identity. But in a quotient, that means that we need to show that the coset representatives belong to P sub N of G sub I plus 1. But we immediately get that by the assumption that G sub I over G sub I plus 1 is an abelian group. So you can look at your lecture notes and go over this part of the argument. So we have already proved this part, that the factors of P sub N of G sub I over P sub N of G sub I plus 1 is an abelian group, and therefore this sequence, this chain of subgroups, each one normal in the next one, implies that G over N is a solvable group. So in that case, we get part 1. Now let's go to the second part. So H is a subgroup of this solvable group, and I want to create a chain of subgroups for H so that each one modeled by the next one is going to be an abelian group. And the natural thing to do is to intersect the subgroup with the chain that we already have. So this is the chain that I'm suggesting to look at. So we start with H intersected with G naught, that's going to give me H back, because H is a subgroup of G. And then I'm going to look at intersection of H by G1, and definitely it's going to be contained inside this, and so on till we get to identity. Now, claim is that each one of these subgroups contains the next one as a normal subgroup, and the quotient is going to be an abelian group. In order to show both of them at the same time, we are going to restrict the natural quotient map from G sub I to G sub I over G sub I plus 1 to the intersection of H by G sub I. Okay, so I'm going to look at the intersection of H and G sub I, and then apply the natural quotient map to the abelian group G sub I over G sub I plus 1. So let's denote that still I'm going to fix I and consider this group homomorphism from the intersection of G and G sub I to this abelian group, which is G sub I over G sub I plus 1. And this group homomorphism P sends H to the coset represented by H. So automatically we deduce what the kernel of P is. So H, small h, belongs to the kernel of P precisely when it is inside G sub I plus 1. So that means kernel of P is, so again, H belongs to the kernel precisely when it belongs to G sub I plus 1. That means kernel of P should be an element of the domain which is inside G sub I plus 1. But G sub I plus 1 is a subset of G sub I, so that means that this intersection is intersection of H and G sub I plus 1. So kernel of P is just the next one in this chain. In particular, it's a normal subgroup of H intersection with G sub I. And second, using the first isomorphism theorem for groups, we get that the domain modeled by the kernel of this map is isomorphic to a subgroup of the codomain. Because the codomain, this is my codomain, because the codomain is an abelian group, we deduce that domain modeled by the kernel of this map is an abelian group, because it's isomorphic to a subgroup of an abelian group, and subgroups of abelian groups are also abelian. So altogether, we deduce that H intersection with G sub I plus 1 is a normal subgroup of H intersection with G sub I, and H intersection with G sub I modeled by the kernel, which is this, can be embedded into this abelian group because of the first isomorphism theorem, which is this. And from there, and the fact that this quotient is an abelian group, we deduce that this quotient is also an abelian group. So altogether, we found out that there exists a chain of subgroups for H that's given by this, which starts from H and ends to identity, and each one contains the next one as a normal subgroup, and their quotient are abelian groups. That means H is a solvable group. Okay, so altogether we show that if G is a solvable group, all the quotients of G and all the subgroups of G are solvable. Now we want to show that if I start with a group G, so this G is not necessarily solvable, but if I start with a group G, that a priori we do not know if it's solvable or not, but I tell you that G modeled by some normal subgroup N is solvable, and that normal subgroup itself is solvable, then we can deduce G itself is solvable. Okay, so let's try to prove this. But before proving this statement, let me recall a statement from group theory that tells us about the structure of subgroups of a quotient of G. So this result from group theory tells us that every subgroup of G mod out by N is of the form of a subgroup of G that contains N mod out by N. So again, there is this bijection that sends a subgroup H of G that contains N to the quotient of this subgroup by N. And that would be a subgroup of G over N, and every subgroup of G over N is of this form. So this is a result from group theory, which is not very hard, but it is useful to recall this statement. So there is a bijection between subgroups of G that contain this normal subgroup N and subgroups of G over N. And the bijection is given by sending H to quotient of H by N. Okay, so now let's go to the assumption that we have. The assumption is that G over N is a solvable group, and also N is solvable. But let's start with G over N being a solvable group. Because G over N is a solvable group, by definition, we can find a chain of subgroups of G over N such that every one contains the next one as a normal subgroup and their quotient is an abelian group. But we already know, using this bijection statement that we pointed out, that subgroups of G over N are essentially subgroups of G that contain N mod out by N. So when I tell you that I'm giving you a chain of subgroups of G over N, I'm essentially giving you a chain of subgroups of G that contain N, and I'm modding them out by N. So I'm giving you G naught over N, G1 over N, and so on. So this technique is actually extremely important and useful. You can combine this by strong induction and go, if we are working with finite groups, go to a quotient of finite group, try to get some results about subgroups of that, and then go back to subgroups of G itself, and vice versa. So, okay, so let's go back to the proof. G over N is a solvable group. That means I can find a chain of subgroups like this, so that when I look at G sub I over N and mod it out by the next one, I get an abelian group. Okay, but now here it comes, the so-called the second isomorphism theorem. What is it? This quotient being abelian, we can say that we can cancel out n's. So that's essentially the second isomorphism theorem, which says that G sub I over G sub I plus 1 is isomorphic to G sub I over N mod out by G sub I plus 1 over N. Okay, so we get back to that, but let me point out that because these G sub I's over N's, each one is normal in the, it contains the next one as a normal subgroup, implies that G sub 0 contains G sub 1 as a normal subgroup, G sub 1 contains G sub 2 as a normal subgroup, and so on. And so we start from G, because we had started with G over N, it's a bijection, so the first one should be G, and we end with the identity of G over N. Identity subgroup of G over N means N over N, so we essentially end up with N. So the last one in this chain of subgroups of G end with N, capital N, ends with capital N. Okay, so we get this chain of subgroups of G, and now I want to claim this. Let's recall how we proved second isomorphism theorem in group theory. So essentially we start with the quotient from the numerator, which is less, we start with we want to ignore the denominator that's more complicated, and this is the more complicated denominator. So we start with this numerator, which is Gi over N, and then we notice that G sub I plus 1 contains N. So when I send the coset of N represented by G to coset of G sub I plus 1 represented by G, this is indeed a well-defined map. So here we are using the fact that N is contained, is a subgroup, is a normal subgroup of G sub I plus 1. So that's why this is a well-defined map. Okay, so we get a surjective group homomorphism from G sub I over N to G sub I over G sub I plus 1. And what is the kernel of this map? Gn belongs to the kernel of this map when this coset is the trivial coset. But this coset is a trivial coset when the coset representative belongs to this group. So this means that the kernel is precisely G sub I plus 1 over N. So again, I can use the first isomorphism theorem and deduce that the domain mod out by the kernel is isomorphic to the image, but here the map is surjective, so it's isomorphic to the codomain. And that's exactly the claim that we have over here. So here is the domain, here is the kernel, and here is the image. So we get that I can simply drop out this common denominator n. So g sub I over n is modeled by g sub I plus 1 over n is isomorphic to gi over g sub I plus 1. And notice that this quotient is solvable. That was part of the assumption because we assumed g over n is g sub I. This quotient is abelian because we assume that g over n is solvable. We chose this sequence in a way that this quotient is abelian. So altogether, we end up getting a chain of subgroups of G that starts from G, ends with N, and each one contains the next one as a normal subgroup, and the factor groups are abelian. Okay, now we are not yet there because in order to show that G is solvable, I need to start from G but end to identity and make sure that each one contains the next one as a normal subgroup and the factors are abelian. So far, we went from G and reached to N. Now I want to go from N to identity. But this we can do because we also know that N is a solvable group. Because N is a solvable group, I do have a chain of subgroups that starts from N and ends with identity. Each one contains the next one as a normal subgroup, and the factor groups are abelian. That's good. Now I can concatenate these two chain of subgroups, start from GIs, and then continue with N sub i's, and go from G to N, and then go from N to 1. Make sure that each one contains the next one as a normal subgroup, and each one modeled by the next one is an abelian. So all together, we get that G is a solvable group. So this shows that if I give you a group and I tell you that it has a solvable subgroup, solvable normal subgroup, and G over N is also a solvable group, you can deduce that G is a solvable group. Okay, so this is going to help us to show that if I give you a solvable, but at the same time simple group, it has only one possibility. It should be a cyclic group of prime order. So essentially, being solvable and simple, they are not quite compatible with each other. Saying that something is simple says that you cannot have many normal subgroups. In fact, only trivial or the entire thing. Saying that it's solvable, it gives you a chain of normal subgroups. Okay, so not all of them are normal inside G, but you have at least one non-trivial one, and then you can go further and so on. Unless your group is a cyclic group of prime order. Let's see how the proof goes. So suppose G is both solvable and simple, and we want to show that it is a cyclic group of prime order. Okay, so knowing that G is solvable means what? Means that I can start from G and get a chain of subgroups and get to identity in a way that G sub I over G sub I plus 1 is abelian. Without loss of generality, I can assume that these guys are strict. So that means if I take the immediate next one and I call this guy N, I end up getting a proper normal subgroup N, so that G over N is an abelian group. So this is the first statement that I wrote over here. Because G is solvable, there exists a proper normal subgroup, capital N, so that G over N is abelian. Okay, so we can find such a normal subgroup. But remember, as part of our assumption, G is also simple. That means it does not have a non-trivial normal subgroup. Now, knowing that N is a proper subgroup, is a proper normal subgroup, together with the assumption that G is simple, we deduce that capital N should be the trivial subgroup. So again, it does not have a non-trivial normal subgroup, and N is normal, and it is proper, so it should be just identity. Okay. What does that mean? This means that G itself is abelian because G modeled by N is abelian. So G is abelian. But remember, when I give you an abelian group, every single subgroup is normal. So every subgroup is normal. But G is also simple. This means that it does not have a non-trivial normal subgroup. So it does not have a non-trivial subgroup. I can drop the normalness assumption. So because I'm telling you that it does not have a normal subgroup, it does not have a non-trivial normal subgroup. At the same time, I'm telling you that every subgroup is normal. So that means that it does not have a non-trivial subgroup. So again, so G is simple. That implies that it does not have a non-trivial normal subgroup. So altogether, we deduce that G does not have non-trivial subgroup. But what does that mean? This means as soon as I pick an element inside G and I tell you that it is not 1, then the group generated by that element would be a subgroup. It cannot be non-trivial. It should be everything. So as soon as I give you an element inside the group which is not 1, then the cyclic group generated by G should be the entire group G. So the cyclic group generated by G should be the entire group G. So every non-trivial element generates G. So if I give you an element G, then G squared should also generate G, unless G squared is identity. So this means what? This means G squared, the group generated by G squared, should contain G. In particular, G should be torsion, no matter what. So again, if G squared is identity, I'm done. If G squared is not identity, then the group generated by G squared should be the same as the group generated by G, which means G is torsion. So, or alternatively, I can argue it like this, that if G is not torsion, then the cyclic group generated by G is essentially Z, and the cyclic group generated by G squared is isomorphic to the even numbers, which is a proper subgroup. It's not going to be the same. You pick your method. In either case, what I'm arguing is that order of every non-trivial element, order of every element is going to be finite. You don't have an infinite order element inside this group. Now, suppose P is a prime order, is a prime factor of this order by Cauchy's result, or here we don't need Cauchy's result because it's cyclic. In either case, you can argue and deduce that there exists an element of order P inside this group. So either you can use Cauchy's result or just raise the element G to some power, essentially order of G divided by P, and get an element of order P. But remember, every non-trivial element generates G. So that means G is generated by an element of order P, which means G is a cyclic group of order P. And that's exactly what we wanted to show. So we end up showing that a solvable simple group is always a cyclic group of order P for some prime number P. Okay. In particular, my claim is that this implies A sub n, the alternating group, and the symmetric group are not solvable groups if n is at least 5. And this result is based on a theorem from group theory, which says the alternating group A sub n is a simple group if n is at least 5. So I'm not going to prove that the statement. This is a result from group theory that I'm relying on, that A sub n is simple if n is at least 5. It's a non-abelian simple group when n is at least 5. Okay, so I want to use this result and show that both alternating and symmetric groups are not solvable. Okay, let's see how the proof goes. So again, A sub n, the alternating group, if n is at least 5, is a non-abelian simple group, and therefore it cannot be solvable, because solvable simple groups are cyclic groups of prime order. But A sub n is not cyclic, it's not abelian, so it's not cyclic, and so it cannot be solvable. So A sub n is not solvable in this case. How about S sub n? If S sub n was solvable, then every subgroup of S sub n is solvable. So A sub n should be solvable, but A sub n is not solvable. Therefore, S sub n is not. So again, because A sub n is a subgroup of S sub n and A sub n is not solvable for n at least 5, S sub n, the symmetric group, is not solvable either. So this completes the proof. And this provides us a good example, a set of good examples for non-solvable groups. Therefore, to show existence of polynomials that are not solvable by radicals, it's enough to find polynomials where the symmetries of the splitting field is isomorphic to either alternating or symmetric group with n at least 5. So that way, we get that automorphisms of K over F, F automorphisms of K is not a solvable group, and therefore the polynomial small f cannot be solvable by radicals. Okay, so we need to find such things. But to do so, first, we are going to make a concrete understanding of the group of automorphisms of a field, F automorphisms of a field, where this field is a splitting field of a polynomial. We have already discussed this in many proofs, but let's make it concrete. And this way we are going to think about the group of F automorphisms of a field of a splitting field of a polynomial as the group of permutations of zeros of this polynomial. This is actually closer to how Galwan thought about these groups. In fact, at that time, group theory had not been developed systematically, and Galwan worked with these permutation groups. Okay, so what's the statement? The statement is that if I start with a field and a polynomial, and if K is a splitting field of this polynomial, then what does that mean that it's a splitting field? It means that I can consider the set of zeros of this polynomial, and let's call it X, as a subset of this field, a splitting field. And this splitting field is generated by the base field capital F and the zeros. Now, and these are the zeros, which means the polynomial can be factored into the linear factors x minus alpha i's, and K is generated by the base field and alpha i's. That's the definition of being a splitting field. Now, what is the statement? The statement says that if I start with a group of F automorphisms of K, I give you an F automorphism, you just ask yourself what it does to elements of X. And it turns out that it's going to send these zeros to themselves, and it's going to be a permutation. Again, we have seen this argument again and again before, but I'm going to go over the argument and make sure that all of us know what it is. So we are going to denote this restriction by R, as always, restriction, and that means R of theta takes theta and restricted with set X. I have to argue why theta of X is a subset of X, therefore restriction of theta to X actually gives me a function from X to X. And second, I have to argue why theta restricted to X is actually a bijection from X to X, and therefore it does belong to the symmetric group of X. Okay, so these are the things that I have to argue. And my claim is that it's not only well-defined, but it is also injective and a group homomorphism. So it's an injective group homomorphism. So that way I can think about the group of F automorphisms of K as a subgroup of, as a permutation group, as a subgroup of symmetric. Okay, so that's the first part. And the second part is, so here the way that I'm defining this group of automorphisms seems to depend on the choice of the splitting field. The second part essentially says that it does not depend on the choice of a splitting field. So no matter what splitting field I pick, let's pick another one, K prime, then the group of F automorphisms of K is in fact isomorphic with the group of F automorphisms of K prime. So this means that this group, at least up to an isomorphism, does not depend on the choice of a splitting field. If I choose two different splitting fields, I end up getting two isomorphic groups. Okay, so that's the second part of this proposition. Let's start with the first part. Starting from an F automorphism of K, we have already discussed that when I apply this to a zero of a polynomial, it's going to give me a zero of, when I apply theta to the polynomial. But notice, theta F is F linear, and the polynomial F is inside F bracket X. Therefore, theta small f is small f. So altogether, I'm getting that theta of alpha I is still a zero of f. So that means as I apply theta to x, I end up getting a subset of x. But remember, x is a finite set, is the set of zeros of this polynomial. It can be at most degree of f. Remember, it's a field, it's an integral domain. An integral domain, a polynomial of degree d has at most d zeros. So x is a finite set. Theta sends x to itself, and theta is injective. Theta is a bijection from k to k, therefore it's an injective map when I restrict it to the set x. So theta is injective, it sends x to x, as x is a finite set, therefore it is also surjective. So that means theta is a permutation of the set x. So x is finite, theta is injective. So essentially we are using pigeonhole and whatever, we deduce that when I restrict theta to x, we get a bijection. So restriction of theta to x does give me an element of the symmetric group of the set x. And whenever the restriction is a well-defined map, we always get that restriction of composite is equal to composite of restrictions. And that means that the restriction map, whenever it is well-defined, gives us a group homomorphism. Now, remember that the field K is generated by the base field and zeros of this polynomial, because capital K is a splitting field of this polynomial over the base field F. That means this. Now, whenever I give you an F automorphism of the field K, it is uniquely determined by its values on alpha 1, alpha 2, alpha 3, alpha n, because this part we already know. As soon as I know what it does to these generators, I completely understand what theta is. So the value of theta, or the theta itself, is uniquely determined by its values at these zeros. What does that mean? This means if I understand what theta restricted to this set of zeros is, then I understand what theta is uniquely. There is only one option for theta. That exactly means that restriction of theta to the set x is an injective map. So if I understand what theta restricted to x is, I do understand what theta is. So R is an injective map. So that means the group of F automorphisms of K can be viewed as a permutation group, can be viewed as a group of, as a subset of the symmetric group of the zeros of the polynomial F. Now let's see why this group up to isomorphism does not depend on the choice of a splitting field. Suppose K and K prime, both of them, are splitting fields of this binomial small f over the base capital F. We have already proved uniqueness of splitting fields. What does that mean? This means we have proved that there exists an F isomorphism from the first splitting field to the next one. So let's call this isomorphism sigma. Now I want to give you an isomorphism from the group of F automorphisms of K to the group of F automorphisms of K prime. What is this C? So in this diagram, you essentially can see what this C is. I am giving you an automorphism from K to K. We already know that K is isomorphic to K prime, and I take two of these. Now from here, I want to give you an automorphism from K prime to K prime. I can essentially go by inverse of sigma, then go up via theta, and come back via sigma. So all together, so again, we go through inverse of sigma, we go up through theta, and then we go back using sigma. So altogether, we get a map from K prime to K prime. And because both sigma and theta are F isomorphisms, their composite is going to be, again, an F isomorphism. So the thing that we end up getting is an F isomorphism from K prime to K prime. And an F isomorphism from a field to itself is called an automorphism, an F automorphism. So when I defined C of theta to be going through sigma inverse and then applying theta and then applying sigma, this C of theta is indeed an element of this group, is indeed an F automorphism of K prime. Okay, so it is a well-defined function. Now, we also notice that I can do the backward of this, meaning instead of going from F automorphisms of K to F automorphisms of K prime, I can go the other way around and go from F automorphisms of K prime to F automorphisms of K, and essentially do this kind of reverse argument. So instead of, I can go this way via sigma, go up and then go back. And that's exactly what I've written over here. Go through sigma and then go up through theta prime, then go back. So if I send theta prime to this composite, that would be inverse of C. So that shows that C is indeed a bijection, is a well-defined bijection. Okay, so now the last thing that we need to check is why C is a group homomorphism, which is rather easy. Let me quickly show you why this is the case. So you've seen similar things in group theory before, but let's check it. So I give it theta 1, O, theta 2, and then I need to see why this guy is equal to sigma O theta 1 O sigma inverse, composed with sigma O theta 2 O sigma inverse. And notice that these two cancel each other out. This sigma cancel out this sigma inverse, and I get exactly this theta 1 composed with theta 2 as we have them over here. So we immediately get that this map is indeed a group homomorphism. It's a bijective group homomorphism. It's a bijective, well-defined group homomorphism. And that's exactly what we wanted to show. So that overall, we end up getting that this group of permutations up to isomorphism does not depend on the choice of a splitting field. If I choose two different splitting fields, I still get two isomorphic permutation groups. So this permutation group, which is essentially image of R, we are going to denote by G sub small f. Sometimes we also emphasize on what the base field was, and we include the base field over here. So by the previous result, this is this is exactly a well-defined group which is independent of the splitting field, and it's a subgroup of the symmetric group with degree of f symbols, because the zeros of f is at most the degree of f, and we get that it can be viewed as a subgroup of the symmetric group. And moreover, this group is just only depends on the polynomial and the field, at least up to an isomorphism, because it does not quite depend on the splitting field. As I change the splitting field, I end up getting two isomorphic groups. And I can summarize Galois solvability theorem by saying that a polynomial f is solvable by radicals over a base field capital F when, if it is solvable by radicals over this base field, then this group is a solvable group. This group sometimes we refer to the Galwan group of the polynomial f over the base field capital F. And this theorem that we proved for the Galois theorem, we discussed it when the characteristic is 0. When characteristic is positive, we have to be careful. It should not be one of the small primes depending on the polynomial f. Okay, so we showed this direction, but still we haven't provided an example where the Galois group of the polynomial is not solvable. To do so, the next lemma, we proved the next lemma. Again, you have seen this next lemma before. We have discussed it earlier, but let's go through the lemma because it's an important example. So suppose I give you a polynomial with rational coefficients, and I tell you that this polynomial is irreducible in Q bracket X, and I tell you that the degree of this polynomial is a prime number P. Now, another important part of information that I'm going to give you is that this polynomial has precisely two non-real complex zeros, and the other zeros are real. So there are two non-real complex zeros and p minus 2 real zeros. So that's the assumption on the group, on the polynomial. From here, we want to deduce that after I label the zeros, so there are p zeros, I can label them by numbers 1 dot p, and then think about the permutation on these zeros as permutations of the numbers, of the labels that I'm going to put them. So that way I can view the Galois group of the polynomial that we denoted by this. Let me also include Q over here. In this particular lemma, I'm going to drop Q and don't write it again and again. We already know that the base field is Q, but we can view this as a subgroup of the symmetric group S sub P. And claim is that I can label the zeros in a way that this P cycle and a transposition are inside this Galois group of this polynomial. So I can label the zeros and make sure that 1, 2 dot p and 1 comma a, both of them are in this Galois group. Okay, so that's the claim. Let's see how the proof goes. We start with definition of a splitting field and G sub f. G sub f, after all, is coming from the action of the splitting action of the group of automorphisms of a splitting field over the zeros of the polynomial f. Okay, so let's say K is a splitting field of this polynomial. That means the polynomial can be written as, okay, so the leading coefficient times these degree 1 factors, x minus alpha 1, x minus alpha 2, x minus alpha sub p, and I'm going to change the order of alpha sub i's later, but for now, these alpha sub i's are inside complex numbers, and the field generated by these alpha i's and the base field Q is a splitting field of this polynomial f. And we are interested on the group of automorphisms of K over F. So this curly G sub F is the subgroup of permutations of the zeros that is induced by elements. That this subgroup is induced by the group of Q automorphisms of K. Notice that characteristic is 0 in here, so everything is separable. We don't need to worry about the separability condition. So I'm going to change Galwan normal. I'm going to interchange Galwan normal. Sometimes I use Galois, sometimes I use normal, with understanding that any normal extension is automatically Galois because everything is separable. Every algebraic extension is separable because the characteristic is 0. Okay, so that's a remark that I'm going to make. Now let's go back to the argument. So K over Q is normal because K is a splitting field of a polynomial, and it is separable. The polynomial is separable, therefore the extension is a Galois extension. Now, when I tell you an extension is Galois, that implies that the group of automorphisms of the field extension is the number of elements in the group is the same as the degree of the field extension. Okay, so let's have this in mind. On the other hand, F is irreducible, and alpha 1 is a 0 of this irreducible polynomial. Therefore, the minimal polynomial of alpha 1 is essentially F. So up to the leading coefficient. So if I multiply leading coefficient of F by the minimal polynomial of alpha 1 over Q, I get F. In particular, the degree of the minimal polynomial is the same as degree of F, which is this prime number P. So let's try to understand what's going on. I have this K over here. I have this splitting field. This splitting field does contain alpha I, so in particular it contains alpha 1, and it is an extension over Q. And what we just argued is to saying that the degree of this field extension is P. Now I can use the Tower rule and deduce that P should divide the degree of the field extension K over Q. So I can use the Tower rule, deduce that this degree divides this, but the degree of the first field is the same as the degree of the minimal polynomial. Degree of the minimal polynomial is the same as the degree of F. From there, we deduce that P divides cardinality of the Galwan group. But remember, this G sub F is viewed as a subgroup of group of permutations with P symbols, S sub P. So having a P element in S sub P is quite restrictive. Why is that the case? In order to understand and appreciate this part better, I have to recall a result from group theory. Again, but let me again go through this a bit slower. So P divides cardinality of this group by Cauchy's theorem. Every finite group, if P is a prime factor of a finite group, then G has an element of order P. P is a prime factor of this G sub F. So G sub F has an element of order P. Has an element. An element of order P. Say sigma is that element. So suppose that okay, so there exists an element of order P. So suppose sigma here is that element, and remember that G sub F is a subgroup of permutations of P symbols, S sub P. How did we compute order of a permutation? So the key result is the following, that if you want to understand order of a permutation, you start with a cycle decomposition of that permutation, and then you look at the length of the cycles that you get. Length of the cycles that you get out of cycle decomposition is called cycle type of a permutation. When I give you cycle type of a permutation, you see a cycle of length n the order of a cycle of length n is precisely n. I have to apply it n times to get back to where I started. Now, when I give you two cycles, two disjoint cycles, then if the length of this one is n, length of this one is m, then the least common multiple of them is going to give me the order of the composite of these two cycles. Now, there is this general rule that if the cycle type of a permutation sigma is given by n1, n2, nk, then the order of the cycle, order of this permutation is precisely the least common multiple of the numbers that appear in the cycle decomposition of the cycle decomposition of this permutation. And remember that the length of the cycles add up to p. Okay, so I'm allowing ones in the cycle type. So length of these cycles add up to p, and their least common multiple is supposed to be order of sigma. Now, if I tell you order of sigma is p, then I cannot have all these n's. I mean, I cannot have if one of these n sub i's is less than p, then all of them are less than p. Then their least common multiple can never be p, because p is a prime number, and all the numbers less than p are co-prime with that number. So here is the important assumption that p is a prime number that comes to the picture. Because the least common multiple of numbers less than p can never be p, we deduce that an element of order p in S sub p is definitely a p cycle. So again, if it's not a p cycle, then n sub i's are smaller than p, so then the least common multiple cannot be p. So from here we deduce that order of sigma order of sigma being p implies that sigma is a p cycle. Okay, so sigma is a p cycle. Now I'm close to the labeling that I want, but I still have a choice for the first one. I'm going to choose the first one to be one of the non-real zeros. So I assign the index 1 for one of the non-real zeros, and I call this guy alpha 1. Then I start applying sigma to alpha 1. I know that sigma is a p cycle. So when I apply sigma to alpha 1, I get the next one, then I apply it again, I get the next one, and I repeat it till I get back to where I started. And remember that sigma is a p cycle, so I get all the zeros of this polynomial. All of them appear in this orbit. These are distinct zeros. So these are all the alpha i's. I'm going to relabel alpha i's, call this guy to be alpha 2, call this guy alpha 3, and so on. So I'm going to call sigma of alpha 1 to be alpha 2, sigma of alpha 2 to be alpha 3, and so on. This is how I'm going to label zeros of this polynomial. That way, for sure, sigma is represented by the cycle 1, 2, p. Not bad. So we found the cycle. Now, how about the transposition? The transposition, I mean, so far we have not used the fact that there are only two non-real complex zeros. Here is where we can use that. I'm going to use complex conjugation. Notice complex conjugation is indeed an automorphism of complex numbers. It sends addition to addition and multiplication to multiplication. So it is indeed an element of Q automorphisms of C. Now, K over Q is a normal extension, and therefore restriction of so if complex numbers is an extension of K, so restriction of automorphism of complex numbers to K sends K to itself. So tau restricted to K is indeed a Q automorphism of K. Okay, now what can I say about this restriction? In order to understand it better, we look at the set of fixed points of this automorphism. The set of fixed points of tau, by definition, is the set of real numbers. These are precisely those numbers which are not moved at all after taking complex conjugation. Now, when I restrict this tau to the set of zeros of K, in order to understand the group G sub f, I have to restrict it to the set of zeros. I realize that p minus 2 zeros are real, so they are not moved at all. The other 2 zeros are complex and non-real, so they are moved. So the only possibility is that we are switching the other 2 zeros. So these p minus 2 zeros are real numbers, so they are fixed by tau, and the other 2 we are swapping, so we are getting a transposition. So we are getting a transposition, and we know one of them we labeled by alpha 1. Remember, alpha 1 was one of the non-real zeros of this binomial. So one of them is alpha 1. I don't know what the next one is, but let's call it alpha sub a. So that means that I'm swapping alpha 1 by alpha sub a, as alpha sub a is the only non-zero, is the only non-real zero of f, and real points, real zeros are fixed by tau. So tau sends alpha 1 to some other non-real zero, and there is only one possibility, that is alpha a, which means that the permutation induced by tau on the set of zeros of f is represented by 1 comma a. And that's exactly what we wanted to show. So altogether, we end up showing that if I have such a binomial which is irreducible, degree is prime, it has precisely 2 non-real complex zeros. In that case, the group generated by 1, 2, p and 1 comma a, this group generated by these two is a subset of the Galois group of this binomial. But remember, the Galois group is also a subgroup of S sub p. Now, an important result from group theory implies that the group generated by these two permutations is the entire set, is the entire group of is the entire symmetric group S sub p. And therefore, we deduce that under these assumptions, G sub f q is indeed isomorphic to the symmetric group S sub p. So if f is irreducible, degree is prime, and f has 2 non-real complex zeros, and the rest are real zeros, in that case, G sub f is isomorphic to S sub p. I mean, essentially, we are using this result from group theory and the previous lemma. Now, it is S sub p. We discussed that symmetric groups, when the index is at least 5, is not solvable. So S sub p is not a solvable group, which implies G sub f is not a solvable group when p is at least 5. And by Galois' solvability theorem, we deduce that f is not solvable by radicals. Because if it was solvable by radicals over Q, then G sub f should have been a solvable group, but it is not because it's isomorphic to the symmetric group S sub p, and p is at least 5, and therefore it's not solvable. Okay, so this gives us an example of a degree 5. Okay, so this does not quite give us, but it gives us a method of finding polynomials of the prime degree and p at least 5, where the polynomial is not solvable by radicals. So I encourage you to think about the next problem. You can use Eisenstein's criterion in order to show that this is indeed an irreducible polynomial inside Q bracket X. And you have to use a little bit of calculus. You look at its derivative, find out how many zeros it has, and then use that to show that there are only 2 zeros. From there, you can deduce that the number of real zeros cannot be more than 3. And then you use mean value theorem to actually find out that it does have 3 zeros. I encourage you to work out the details of this and check that the properties of this previous theorem, all of them hold for this polynomial. From there, you can deduce that it is not solvable by radicals over Q. So this would be one of the examples of a degree 5 polynomials that are not solvable by radicals over Q. Because I cannot solve this particular polynomial over Q, that means there is no general rule. There is no general formula in terms of the coefficients, plus, minus, addition, multiplication, division, and taking radicals to solve degree 5 equations. So this general kind of result goes back to Abel that showed that there are no general formula in terms of addition, subtraction, multiplication, division, and taking radicals to solve degree 5 equations. Okay, so now so far we have proved that if I tell you that f is solvable by radicals, then the Galwan group of f is a solvable group. Next, we want to show the converse of this statement, at least when characters, I mean, always we are working with characteristic 0 in order to avoid certain separability issues. So next, we want to show this result. Again, it is due to Galois, that shows that if f is a characteristic 0 field, and small f is a polynomial with coefficients inside capital F, then this polynomial is solvable by radicals precisely when, if and only if, not over Q, but rather over F. So it is a polynomial that is solvable by radicals over the base field precisely when the splitting field, the Galwan group of the polynomial, is a solvable group. Again, we have already proved this direction. And next, we want to show that under the assumption that G sub f is a solvable group, well, how can we show the polynomial is solvable by radicals? Okay, so that means we need to still investigate solvable groups a bit more to get a better understanding of the structures of solvable groups. The next lemma is going to help us to understand structure of solvable groups slightly better, and then we are going to use that in the next lecture to show the converse of this statement, meaning we are going to prove Galois theorem from both directions. Okay, what does the next lemma tell us? It says that if I start with a finite solvable group, okay, by definition, I can find a chain of subgroups where each one contains the next one as a normal subgroup, and the factor group is abelian. But we want to go further and say it's not only we can find a chain so that the factors are abelian, but we can find a chain where the factors are cyclic groups of prime order. Okay, so we start with a finite simple group. Then there exists a chain of subgroups starting from G, going to identity, where each one contains the next one as a normal subgroup, and the factor groups, all of them are cyclic groups of prime order. Okay, so then later we are going to use this, combine it. So assuming that this Galwan group is solvable, we are going to apply this, get a chain of subgroups, use the fundamental theorem of Galois theory, and get a chain of a tower of subfields, intermediate subfields, that start from capital F, ends with the splitting field, where each one is Galois the next one, and the Galwan group is a cyclic group. So this would brings in studying of Galois extensions where the Galwan group is a cyclic group. Instead of just saying that the Galwan group is solvable, we can focus on Galwan group being cyclic. Okay, so that is our plan. Let's start with this lemma though. We want to find this chain of subgroups where the factors are cyclic groups of prime order. Okay, again, let's start with the assumption. The assumption is that G is solvable. What does that mean? It means there exists a chain of subgroups starting from G, ending with identity, where each one contains the next one as a normal subgroup, and the factor groups are abelian. Let's denote this chain by G sub I hats. Now, G is a finite group. That means all these factors are finite abelian groups. So they are finite abelian groups. Abelian groups are definitely solvable. So the question is, can I prove this lemma, not for solvable, but rather for abelian? So if I give you a finite abelian group, can you give me a chain of subgroups where the factor groups are cyclic groups of prime order? So that's the claim that we are making next, that if A is a finite abelian group, then it does have a chain of subgroups that start from A, ends with identity, each one contains the next one. Okay, so here it's abelian, so all the subgroups are automatically normal, but it contains the next one, and the quotients are cyclic groups of prime order. Okay, that's the claim. Let's see how the proof goes. We are going to proceed by strong induction on the cardinality of the group. If the cardinality of the group, if it is 1, there is nothing to prove. So I'm going to go directly to the strong induction step. Because cardinality of the group is not 1, it does have a prime factor p. So again, I can use Cauchy's theorem and find an element of order p inside the group capital A, and let's denote it by small a. So small a is an element of order p. Because A is abelian, every subgroup is normal. In particular, the cyclic group generated by A is a normal subgroup, so I can mod out by this subgroup, and I end up getting another abelian group, but definitely smaller. Now I'm getting an abelian group, which is smaller, so I can use the strong induction hypothesis and get a chain of subgroups for the factor group. So A mod out by this group generated by A contains a chain of subgroups that start from this group, ends with identity, and each one contains the next one. Again, it's abelian, so I don't need to mention the normality, but they are normal subgroups, and the factors are cyclic groups of prime order. Again, let's recall the bijection theorem. We know that all the subgroups, every subgroup of A over A, if I tell you that it's a subgroup of this, then it is of the form a subgroup A sub I of capital A mod out by the group generated by A. So every subgroup of this guy looks like this. So every subgroup of this is the same as H over this, where H is a subgroup of A, and the group generated by A is contained inside H. So the bijection result that we have tells us this kind of description about subgroups of A mod out by the group generated by small a. Okay, so that means A sub I bars, that means A sub I bars are equal to A sub I mod out by the group generated by A, and A sub I is a subgroup of my abelian group, and it contains the group generated by A. Now I'm going to consider this chain of subgroups that we are getting from A sub i's. These are starting from A and end with the group generated by A. And each one contains the next one, and so on. Now, I'm going to add another group, another subgroup to this chain, and that's just a trivial group. I'm going to add it in order to start from A and end with 1. Now I'm going to look at the factor groups inside this chain. So what are the factor groups? The factor group A sub I over A sub I plus 1, by a similar argument by the second isomorphism theorem, this is isomorphic to the factor of A sub I by the group generated by A mod out by the factor of A sub I plus 1 by the group generated by A. But these are equal to A sub I bar and A sub I plus 1 bar. So this means that these new factors are isomorphic to the old ones, at least for the first n factors. In particular, all of them are cyclic groups of prime order. How about the last one? The last one is the group generated by A. And the group generated by A has p elements, which is the cyclic group of prime order. So the last one is also a cyclic group of prime order. Altogether, I'm giving you a chain of subgroups of this abelian group Each one contains the next one, and the factor groups are cyclic groups of prime order. So this gives me the claim. Now I'm going to apply this claim for, again, let's go back. I initially started with the solvable group. I got this chain of subgroups where the factor groups are abelian. Now for these finite abelian groups, I want to use this claim. For each one of these finite abelian groups, I am going to use the claim and get a chain of subgroups where each one modeled by the next one is a cyclic group of prime order. Okay, so let's put it together. Because these guys are finite abelian groups, I can start with them and go to identity and get a chain of subgroups, each one containing the next one as a normal subgroup because it's abelian anyway, so that the factor groups are cyclic groups of prime order. Again, I'm going to use Bijection Theorem and say every such a sub I1, a sub y2, and so on is of the form a subgroup of g sub I hat, a subgroup of the numerator over here, mod out by the denominator, and this subgroup should contain the denominator, otherwise it does not make sense to mod it out. So the bijection theorem that we discussed about the subgroups of quotient implies that every a sub ij is of the form of g sub ij mod out by the g sub I plus 1 hat for some subgroup that's sandwiched between numerator and denominator of this group. And notice by identical argument, I can drop this common denominator and deduce that this quotient group is isomorphic to the quotient of only their numerators, and therefore the quotient of the numerators is still a cyclic group of prime order. Now I'm going to put these, concatenate the chains that we are getting over here. Notice that the chain of g sub ij's start from the numerator here and end with the denominator, because we are starting from this quotient, which means that the numerator should be this one, and with 1, which means numerator of the last one is like the denominator of this beginning. So these g sub ij's start from g sub I hat, end with g sub I plus 1 hat. This is true for each one of these i's. So I can actually concatenate these chains together and get a long chain starting from G ending with identity. So let's see a few of them. So the first G sub ij's, if I start with G sub 0 j's, G sub 0 1 is just G sub 0 hat. And then I go till I reach to the bottom of this part, and I reach to G sub 1 hat. So this is equal to this one, which is also the same as G sub 1 1. And then next one is the same as G sub 2 hat, and so on. So each time we start with this and end with it. So that way we can start with G and get to identity. And remember, each one of these quotients are cyclic groups of prime order. So we get the desired result. We end up finding a chain of subgroups from G to the identity. Each one is normal in the next one, and the quotients are cyclic groups of prime order, and that's exactly what we wanted to show. So in the next lecture, we will focus on finite Galois extensions, where the group of automorphisms of E over F is a cyclic group of, okay, so we can also add prime order, but we don't need it. So we will focus on such extension, and under some assumption, similar to the Kumar extensions, we add enough roots of unity and deduce that in that case, it is a Kumar extension. We will use that to show the converse of the result of on solvability, Galois solvability theorem. Okay, for now.